Hello everyone, we are in the lecture number 15 of thermodynamics. Here our subtopics today are isothermal and adiabatic slopes of the PV curves and adiabatic expansion of ideal gas and their thermodynamic functions. First, the slopes of the PV curves. In case of isothermal expansion, they are called isotherms, these curves. And what is the value of the slope for adiabatic expansion of ideal gas? Let's find it out. In case of isothermal change, PV equals to constant, and let us say it is equal to K. Okay. So therefore, what should be the slope of the PV curve? Definitely it is dP by dV. Okay. If P is in the y-axis and V is in the x-axis, then it is dP by dV. So here we know PV equals to K, that means P equals to K by V. Okay, so in place of P we have put here K by V and then started differentiating, and the result is minus K by V square, and we know K is equal to PV, so we are just putting here PV again, so we get PV over V square with a negative sign, and the final result is minus P by V. Okay, and if this change is an adiabatic change, then what is the value of the slope? In case of adiabatic change, just we have seen in the last lecture that the relationship between P and V is PV to the power gamma equals to constant, where gamma is the Poisson's ratio. Then let us say that this constant has the value K prime. Okay, so let's differentiate P with respect to V, but we know that P equals to K prime divided by V to the power gamma, so we have put this value here and then differentiating this term with respect to V volume. Okay, and the result is minus gamma into K prime over V to the power gamma plus 1. Yes, and in place of K prime we are putting PV to the power gamma. Okay, so we are putting PV to the power gamma here, and the final result is minus gamma into P by V. So both the slopes are negative, but this one is more negative because this is greater than 1, always greater than 1. So the slope of the PV curve in case of adiabatic change should be more steep than the isothermal curve. Okay, so both the slopes are negative. We are drawing the conclusion now. Both the slopes are negative. Here, look, this slope is for the isothermal expansion and this slope for the adiabatic expansion. So this is definitely steeper than this one. Okay, here the value is minus P by V, and here it is more negative than minus P by V, and this value is definitely greater in modulus with greater than minus P by V. Okay, this is minus gamma into P by P. So the coefficients of the isothermal slopes is minus 1. Okay, and the slope of the adiabatic curve is minus gamma when gamma is greater than 1, and the adiabatic slope is steeper than that of the isothermal slope. Okay, so these are the explanations. Simple. This would be used when we will be doing Carnot cycle during our study of second law of thermodynamics. Okay, now our next topic, adiabatic expansion for ideal gas, both reversible and irreversible, and the thermodynamic functions. That means we have to find out the values of delta U, delta H, okay, minus W or Q. And for your information, let me say that both reversible and irreversible processes have the same expressions. So where is the difference? Okay, let me keep you in suspense. I am going to tell this later on. Okay, so U is a state function and it is a function of temperature, pressure and volume, and let's select temperature and volume and apply the slopes rule here. So if U is a function of temperature and volume, then du equals to del u by del Tv dt plus del u by del Vt dV. Okay, but we know that this expression has is equal to Cv del u by del Tv. So we are putting Cv in place of this expression. So it is becoming Cv into dt plus del u by del Vt dV as it is. Now for an ideal gas from the Joule's experiment, we know that del u del Vt equals to 0. Therefore this whole term is 0. That means du becomes Cv dt. Now let's differentiate both sides by giving limits. The lower limit is T1, that of temperature, and upper limit of temperature is T2, and the respective internal energies are U1 and U2. Okay, and the final result is U2 minus U1 equals to Cv into T2 minus T1, and here U2 minus U1 is nothing but delta U. And if there is more than 1 mole of gas, say it is n moles of gas, then it is del U equals to nCv into T2 minus T1. Okay, so this is the expression of delta U. Now adiabatically Q equals to 0. We are going to find the expression of W. Okay, and from the first law of thermodynamics, what? Now Q equals to delta U minus W. So delta U minus W is also equal to 0. That means minus W is equal to minus delta U. Okay. Now the expression of adiabatic work done by 1 mole of ideal gas. What is the expression? The expression is minus W equals to minus Cv into T2 minus T1. Okay, because this is U2 minus U1. So U2 means what? Cv into T2, and U1 means what? Cv into T1. So in place of delta U we can write Cv into T2 minus T1 with the negative sign, and if this negative sign is eliminated, then these two terms would change their positions. That means T2 minus T1 becomes T1 minus T2. So minus W is Cv into T1 minus T2, and if it is n moles of ideal gas in place of 1 mole, then it can be written as nCv T1 minus T2. So this is the expression of work done by the system, which is minus W. So we have got already 3 expressions for adiabatic, isothermal, and reversible and irreversible change. These are dq equals to 0 or q equals to 0, minus W equal to Cv into T1 minus T2, or for n moles of ideal gas it is n Cv into T1 minus T2, and finally and also we have got the expression of delta U, which is Cv into T2 minus T1, and for n moles it is n Cv into T2 minus T1. Now finally the expression of delta H. So delta H is nothing but H2 minus H1. The expression of H2 is U2 plus PV2, and H1 is U1 plus PV1. Okay, so take the U terms together and mechanical energy terms together here. So U2 minus U1, this one, and here PV2 minus PV1. Okay, you can also write U2 minus U1 as delta U, and this one as PV2 as RT2, and PV1 as RT1. Okay, but we know that delta U is Cv into T2 minus T1 from our earlier deductions, and here R is taken as common, then it becomes T2 minus T1. So both T2 minus T1 can be taken as common here, leaving Cv plus R. Okay, so it's product of Cv plus R and T2 minus T1. But we know Cp minus Cv equals to R, therefore Cv plus R equals to Cp. So Cp into T2 minus T1. So the expression of delta H is Cp into T2 minus T1 for 1 mole, and for n moles it is nCp into T2 minus T1. Okay, so that's all. Thank you. Have a nice day.